Okay, pre-calc, part two. Part two is a little bit different because you got two vertical asymptotes now. Nothing changes here. Except now we have to solve a polynomial, which usually, well, they were polynomials before, but this is a sorry, I'm getting tired. Quadratic polynomial. This one ends up being factorable. So -4 times +1 gives me -4, and they also add up to -3. So I've got vertical asymptotes at x equals +4 and x equals -1. So 1, 2, 3, 4. -1. All right, here's something that's kind of tough to explain, but your horizontal asymptote is going to be 0. Here's why. If I'm plugging in a really big number, say 100 billion to the trillionth power, that's a big number. When I square that huge number, it is going to get so tremendously larger than the top that it's just going to eat up any ground that the top made up. The bottom will always dominate the top if the power, right? If its exponent is bigger than the top. So you can test some points. You can test 1,000,000. You can test 1,000,000,000. You can test 1,000,000,000,000. You're going to find that it's zeroing out. It's getting closer and closer to 0. So the x-axis acts as a leveling off point. Now here's the tricky part. Remember when we said the top equals 0 is a 0? It still technically is. X equals 1 is a spot where your graph crosses the crosses the x-axis. How can that be? Well, we're going to find out here. So we know we have a point there. Let's plug this puppy in the table and see what we get. So we've got x minus 1 up top. On the bottom, you've got x squared minus 3x minus 4. All right, let's start the table. Let's figure out what's going on in between these two asymptotes. So I'm going to check out 0. 0 gives me a quarter, 0.25. -0.25 gives me a little bit higher. -0.75 gives me all the way up to 1.47. And then when I plug in points in between -1 and -0.75, they get astronomically bigger. So basically, here's what's happening. It's getting closer and closer to -1, but never touches. And then comes down here like this. Now, if I plug in 1, I get my 0 here. And then after that, they turn negative. Wow. So 2 gives me -1/6. 3 gives me -1/2. 3.5 gives me -1.1 repeating. 3.75 gives me -2.3. And as you can see, the curve is basically forming another kind of like asymptote hugging plot of points. Weird. It kind of looks like a cubed type function, but it acts just kind of on its own. Interesting. I wonder what the ends are going to look like. Let's plug in -2. You get -1/2 when you plug in -2. Is this one going to cross over? -3 is -0.3. Well, I don't think so because there's no more zeros. That was the one zero that we could compute. All right, we're getting closer and closer and closer to 0. -7 gives me -0.1212. And if you plug in -1/2, you almost get -1. And it drops. Interesting. Now, what's it going to look like on the other side? Just plug in 4.5. 1.27. 1, 2, 3, 4.5, 1.27. If you plug in 5, you get 2/3. You plug in 6, you get 0.3. And with more point plotting confirmation, you can see what's going on here. All right, so can we glean any lessons from this? Looks like the X here on top is creating a separation between these two. I don't know. We'll do more analysis in class because we're already 7.5 minutes in the video. We got to get this last one done. All right. Oh, my goodness. The last one looks complicated. As if the others didn't, right? All right, so I'm going to go out of order this time. Let's do zeros first. Top equal to 0 gives us our zeros. Hey, difference of perfect squares. 1 minus x, 1 plus x. We got 2 zeros. One at +1, one at -1. Vertical asymptotes. Set that bottom equal to 0. Factorable. X minus 3x plus 1. +3, -1. Wait a second. How can I have a 0 and an asymptote in the same spot? You know, let's take a look at this function more closely. Here's the factored version of it on top. Here's the factored version of it on the bottom. Notice anything? I can rewrite the top as x plus 1. Anything divided by itself is 1. Okay. What we're seeing here is that there is a hole in the graph. It's a poser 0. It's not an asymptote, and it's not a zero. It's a hole in the graph where nobody lives at that one tiny spot. Weird. Okay, so that leaves us with one asymptote here. Our vertical asymptote, well, I mean, I see a negative 1 over 1 here as the ratio of the leading powers. And if I plugged in a billion on for every x on top, and as I did on the bottom, then you're going to see, oh, it's looking like it's getting really close to negative 1. So I've got a horizontal asymptote at y equals negative 1. I got a vertical asymptote not at negative 1, nor do I have a 0 at negative 1, but I still got one at 3. So because we have a 0 up here, my thought is that it's probably going to do this and this. Let's check it out, though. So I'm going to plug in the original equation into my graphing calculator for the table. You don't need a graphing calculator to do this. You just need a calculator with a table. X squared minus 2x minus 3. So let's plot some points here. 1, 0, knew that. 2, 1. 1.75.6. 2.53. All right, it's escalating now. 2.75 is 7. What? All right, so it's pretty clear there. Hey, this is interesting. So it doesn't look like the hole in the graph. This is interesting. If I go to, so here's 0. Negative 1/3, right? Negative 0.3 repeating. Look at negative 1. They just put an error on the calculator, because it's not an actual y value, you know? But here's where the y value should be. You see this function right here? We could plug in where the poser is into this reconfigured function. What's 1 minus negative 1 over negative 1 minus 3? It's negative half. Yeah, so this error right here, that should be y equals negative 1/2. So the hole in the graph is at negative 1, negative 1/2. So there's sort of like a fourth piece of information that's kind of helpful. At x equals negative 1 and y equals negative half. So it's pretty much this function. 1 minus x over x minus 3. It's just there's a hole in the graph. And then again, we could flesh out the curve beyond 1, 2, 3 very easily. 3.25 is negative 9, way down there. 3.5 is negative 5. 4, negative 1, 2, 3. 5, negative 2. Okay. All right. Wow. Okay, so that was exhausting. Rational functions are not the most fun math lesson, but I hope you guys learned something from this, and you enjoyed my antics with this calculator. So thanks for watching.